Start to get very difficult to keep track of what's going on. So here's a little kind of summary. At the end of class last time we were talking about the work integral, right? And we defined it to be this right here. And we said that if we use our scalar notation, this work integral becomes this. So if we look back into the two-dimensional case, this is three-dimensional. If we look in 2D, our work integral, so the work done by the field F over the curve C, moving an object through this along this path, would be equal to this. All right. Now, if we close this curve, then this work integral becomes this line integral, which by Green's theorem becomes this double integral. So we are talking about work if we can use this for work if it's closed, if it's a closed path.
And if it's closed and conservative, it's going to be 0.
If it's closed and conservative, it's 0. Now, let's say that this right here, we want to do this, and it's not closed, but it's conservative. Then we can use the fundamental theorem of line integrals and just evaluate at the two endpoints, right? So there's a lot of different little branches of possibilities here, right?
Sorry about that.
No, that works. That works. I can do I can do this. I can do this and move across the. All right. Were you listening to music, or was that a movie or something? No. So I'll tell you this quick story. One of the first classes I ever taught was at a university, and they had just hired me on like at the last minute. I was in graduate school, so they needed someone to teach. I don't even remember what class it was, but so they had gotten, you have to get all your credentials set up so that you can log into the computers. So I go and first class, I go set up I go to the little podium and I'm logging in. It won't take my login. So I'm like, shit, and I have everything I'm going to project. So I open up my laptop real quick, and I've already eaten up like 5 minutes of class. Open up my laptop and I plug it into the display, and I'm fumbling through my books and stuff. And I had my screensaver was a picture of my girlfriend and I, who's now my wife, but at the time was my girlfriend. And it was not, it wasn't inappropriate, like there wasn't any like nudity or anything, but it was not the type of picture you just want to present in front of an auditorium of people, right? That was like my first time ever teaching, It wasn't my first class ever, but it was one of my first semesters. And so I was like, people started laughing and stuff, and I'm like, what are they laughing at? And then I look up, oh shit. So it turned out there was a graduate student that was in that class sitting there. They were like, I don't know why that they were in there or whatever, but they went and complained to the dean of the department that I had put up like pornographic material and stuff, and I was like,
There's that one
what?
kid. There's always that one kid.
I was like, so I sat down with the dean, and he and I were real good friends. We were close and everything, and I showed him the picture, and he's like, who cares? It wasn't bad. It was just just a picture. It's like a picture of you and your significant other, showing each other a little affection. Someone took a picture.
Remember, kids, if you have a significant other, don't show any affection whatsoever.
So that made me think of that. You're sitting there, and all of a sudden, we get to.
Stop it because I didn't know what it was.
Yeah, I couldn't stop it either. It was there. I couldn't do anything about it. All right, so here we go. 13.4, Green's theorem. Okay, so what we've seen is that, I'm recording? Okay, what we've seen is that if we have a line integral over a closed curve, that we should be able to use Green's theorem if need be. We can try it. But sometimes we can start with a double integral and turn it into a line integral and using the same theorem backwards. But there's some things that have to be tweaked just right. And that's because you're starting with partials here, right? You'd be starting here and going back to this. Here you start, they give you the field PQ. You've got that. You can take partials. But to go from here backwards is a little different. So here's how this is going to work out. Remember, we've had this integral in the past. We've used it twice already today. That the area of D is the double integral over D of 1 dA, right? So we are going to focus just on, right now, just on how could we use this to help us solve this, all right? Okay? If we ever needed to do this, could we use Green's theorem? So this integral right here, this double integral, is looks exactly like Green's theorem if this partial q with respect to x minus partial p with respect to y is 1, right? If this difference right here is 1, then that's what we have, right? So the question becomes, when would this ever be 1? And there's a couple of ways it could happen. So let's say I sit here and I define p to be 0 and q to be x. Then what is the partial of q with respect to x? 1. And then what's the partial of p with respect to y? 0. And so if p is 0 and q is x, then Green's theorem would give us a 1 there, and then we would basically have that, wouldn't we? Now, you could do it some other ways. You could let p be negative y and q be 0. So what would happen if p is negative y and q is 0? So partial of q with respect to x would give you 0. And then you're doing minus the partial of p with respect to y, which would be negative 1. So you get negative 1, which would give you 1 also, right? And then, I mean, there's actually a lot of different ways you could do it. Here's one more. You could let p be negative 1/2 y and q be 1/2 x. And if you do those partials, put it into this formula, you would also get a 1. All right? All right, so that means that if we ever want to do this double integral, I'm going to put this over here, double integral over d of 1 dA, if we're ever trying to do this, that we could use a line integral along C on the closed curve. We could use this first method, which we would have to do x dy. You understand where this x dy comes from?
Yeah.
Sure? Yes, it's this formula going back to here, replacing everything p and q with what we said it had to be. So we could do that, or if we didn't like that, we could do the line integral along C, the closed curve, of the second one, which would be negative y dx. Or we could do the last one. I'm not going to write that one down. Okay? So let's see how we might be able to use this. Find the area of a circle with radius r. Now, I proved this to you already, didn't I? I proved this formula using a double integral in polar coordinates. So let's take a look at this. We have a circle, has a radius of, I'll use little r, radius of little r, all right? If we want to know this, we could do the double integral over d of 1 dA, right? Where d is this in here. And that right there would give us the area of that, right? But according to what we just said, we can always transform this double integral into one of those. So let's go with the first one. This should become the line integral over the closed curve C of x dy. But now we're talking about C. And C is the curve that encloses D, right? So let's do this line integral. And we're going to do it just the way we did these before. We're going to find a parametric representation of C. So C here would be x is some function of t. What would it be? And what's y as some function of t? So cosine t, sine t, but we want the radius to be r, right? So r cosine t, r sine t, right? And t is going to go between 0 and 2 pi. Agreed? So we should now be able to go here, make this go from 0 to 2 pi, replace x with our x function of t, which is r cosine t, and then replace y, not replace y, dy is next, right? So derivative of this with respect to y, derivative of y, so derivative of this with respect to t, which would be r cosine t dt. Now r is a constant, right? So I'm going to pull the r out. I'll have r squared, integral 0 to 2 pi, of cosine squared t dt. And to do that, we would power reduce, right? Use our power reducing formula. So I'm going to pull a 1/2 out of everything. R squared integral 0 to 2 pi. That becomes 1 plus cosine 2t. You understand what I'm doing there? Using the formula that has a 1/2 in it so it comes out. And then integrate each of these respectively with respect to t. So where am I at? 1/2 r squared. Antiderivative time. So antiderivative of 1 with respect to t would be just t. And then the antiderivative of cosine of 2t should be half, right? 1/2 sine 2t. And we're evaluating this from 0 to 2 pi. Agree? What should our answer be? Pi r squared. Is it going to be? 1/2 r squared. Okay, what happens when we plug in 2 pi? We get 2 pi plus sine of 4 pi is 0, so that's gone. And then when we plug in 0 here and 0 here, they're both gone. So all we wind up getting out of this is 2 pi. And then the 2 and the half cancel, and you just get pi r squared. So not a coincidence. That is one illustration of how you can transform a double integral where you're trying to get area into a line integral around the edge. Yes?
So could you use the other equation?
This one right here? Yep, and you get the same answer. So let's just set it up real quick. How would it differ? You would still have 0 to 2 pi, but now you're using negative y. What's negative y? Negative r sine t, and then dx this time, which would give you another negative r sine t dt. You could pull out a negative r squared, and then you'd have sine squared, and then when you did that one, you should get the same result. Do you want me to take it, or you trust that it would, or you're okay with that? Okay, but you know what? We could have done this with a double integral anyway, right? So maybe there's another example that would be more constructive, like this one. Find the area of the figure below, which is called an epicycloid, which has as its parametric equations hide this, get it out of here. So we want to find the area of this, right? And that's kind of a messed up looking shape, right? To find the area of that seems like it would be extremely challenging. And we're getting the shape by graphing this curve, right? Graphing that curve. And that draws this shape. It's a closed curve, and we want to know the area inside of it. So if we were stuck with double integrals, or even Cal 2 stuff, we would be pretty stuck at this point. Because these regions, like you couldn't look at this region as a polar region, as a type 1, as a type 2. It doesn't fall into any of those categories. Does that make sense? So let's use this. the area of D, the area of this is 1dA, right? Double integral over D of 1dA. But if we look at the curve, C, then we can turn this into a line integral along the closed curve C, and then we have those formulas again, which I just erased. That was very smart of me. What was the first one? X dy?
Yes.
Right? X dy? So we can do this x dy, right? Now, the give and take on this is, in order for us to use this, you must be able to come up with a parametric representation of C. But we were given that because that's how we drew the shape, right? So this is perfect for this because we have x as a function of t, y as a function of t already. You'll see that? And we're given the restrictions. So we can go right to the integral now, integral 0 to 2 pi, and then it's going to be x, which is our 5 cosine t minus cosine 5t, right? And then times dy, which is the derivative of this one, right, with respect to t, which is 5 cosine t minus 5 cosine 5t. dt. Understand? X dy. And now, as long as we can integrate that, we're in business. So how about we pull, we can pull a 5 out of this one, right? Just out of that one, but not out of this one. So I'll just pull a 5 first. Five cosine t minus cosine 5t, and then times cosine t minus cosine 5t. How would you go about doing this one? Kind of have some different options here, but you want to just expand it all out?
Yeah.
Just like multiply it all out? We can do that. This isn't going to be a fun integral, but at the same time, we're finding the area of a pretty weird shape, right? I mean, it should require some effort for this. So integral 0 to 2 pi. All right, we've got the 5 outside, sorry. And then 5 cosine squared t. And then 5 cosine, so minus, right? 5 cosine t cosine 5t. The middle one is minus cosine t cosine 5t. And then our outer ones there plus cosine squared 5t. dt. We can combine the middle terms. Oh, and the end term. No, they're not the same. Oops. Yeah, these two can go together, right? We can do this with a power reduce, right? And we can do that with a power reduce. And then how are we going to handle this one? I'm just going to save myself a little bit of time, I'm going to just erase that and put minus 6 cosine t cosine 5t. Any ideas? I mean, so can I put a check here? We could do that with power reducing. And a check here with power reducing?
Yeah.
Okay, but what about the middle one? Any ideas on that? We could go to our pre-cal, and we could use our product to sum formulas. So who has their formula sheets? I think it's in our calculus formulas. We have our trig formulas. Yeah, look in there. Algebra. All right, here we go. I don't see them here. I don't see them on this page. Okay. So there's this place called Google, right? But there's a formula for this that takes a product of two cosines and breaks it up into a sum. And then you could do that one. Now I'm just going to have the computer do it. Is that all right? We had a 5 on the outside. We were going from 0 to 2 pi. All right. All that, right? So 5 cosine, that's not a 5. 5 times cosine t, that squared, minus 6 cosine t times cosine 5t plus cosine of t, is that 5t squared? Yeah. 5t squared dt. Does that look right? Does it look like this? All right. It don't like me. 30 pi. All right? So pretty cool that we can use that Green's theorem backwards to find the areas of some pretty crazy shapes. This is work, right? This is work, two-dimensional space. We want to find the work done by this field as we move an object along the path C. Here's our vector field. C is this triangle. I think we should start by drawing the triangle, just to see what C looks like. So C is going to start from 0, 0. It's going to go to 2, 6. 6, so 2, 6. Then go to 2, 0. And then go back to 0, 0. Now remember, this is actually the line integral along C of p dx plus q dy, right? That's the same thing written out of vector notation into our scalar notation. But this is this Green's theorem if it's a closed curve, which it is, right? It's a closed curve. However, we have negative orientation because it says here the triangle from 0, 0 to 2, 6 to 2, 0 and then back. To use Green's theorem, we need it the other way around, right? So if we're going to use greens, we just need to change the orientation. We just need to reverse the path, which means change our answer by a negative sign, right? Just multiply by -1 at the end. So the way I'm going to do this, I'm going to work it out just as it is, use Green's theorem, go straight through it, and at the very end, I'm going to just switch it to negative. Or if it's negative, it'll become positive. If it's positive, it goes to negative, all right? Now, do you like the idea of doing greens, or do you just want to stick with the line integral? Maybe it's better if we leave it as a line integral. What would be the drawback if we do line integral?
If it's not such a simple shape, it get more a little more complicated.
Yeah, look at this. This is our path C, right? And C is made up of 3 line segments, which means you need to break this line integral into C1, C2, C3. You'd have to go and find a parametric representation of from here to here, and then from here to here, and then from here to here. We did that last class, but we would have to do that here, and it would be, I mean, we can do line segments, but it's kind of a pain in the ass, right?
Yes, I think green's theorem would be the best.
Green is nice because look at the area that's enclosed here. Look at our region D. Do you mind doing a double integral over that region? If we have to do a double integral over that region is at least like a type 1 region, right? Our x's are between 2 constants, our y is between 2 functions of x. We should be able to handle that double integral. But maybe we'll get even luckier because when we do our partials, maybe the partials here are going to wind up making these things a lot nicer. I don't know yet. We're about to find out. But I'm going to go to greens because it is closed, right? So greens, this can become double integral over D. P here is this. Q here is this. So the first part is the partial of Q. Partial of Q with respect to x. Maybe it's not as nice as we were hoping. Partial of Q with respect to x would be 2x plus 2y cosine x. I'm not liking that. But then minus now the partial of P with respect to y, which would be 2y cosine x. Look at that. It's almost like they made the problem to work out nice for us, right? And they did. They did. Right? This, look at that. These are gone. And so all I'm integrating is 2x. Sure, I wish it was 1. Don't you wish this was a 1 or a constant? Because then you can just pull it out and you're just saying it's whatever the constant is times the area of D, and I think we could all find the area of that triangle easily. But there's an x in here, so we have to go through it like we did double integrals from the very beginning of double integrals. So I like greens. We're going to stick with greens, okay? So this is now double integral over D of 2x with respect to area. So now we look at our region D. We need to find our restrictions on x and y. Right? No need to go to polar here. No need, in fact, you wouldn't want to go to polar. This is a perfect type 1 region. Our x's are between 0 and 2. And our y's are between 0 and, well, whatever that line is, right? 0 and, what is that line? Yeah, it has a slope. It rises up 1, 2, 3, 4, 5, 6 and goes over 2, so a slope of 3. Y-intercept of 0, so 0 to 3x. So now I can put the limits of integration on here. Do I have the freedom of changing the order of integration here?
No.
I do not. So it has to be 0 to 2 on the outside, 0 to 3x on the inside. It's got to be dy first, then dx. And I think everyone could handle that. I know my computer can. So we'll just get an answer that way. I know you like to go home and do these on your own, the ones I don't do in class. Sorry. Zero to 2, 0 to 3x, no, 3x. Integrating 2x, dy dx. 16. Sorry, can you not see it? Where the hell is it? Oh, it's right here. Yeah. Right there. Okay, so you should get 16 when you do that. So that means if we go back to the original problem, what we're saying is that if you were to take a particle, right, and move it along this curve through that vector field, then the work done would be 16. All right? 16, then the units would depend on how you want to measure your work. And that would also depend on a lot of other things, like what you're given, pounds, feet, you know, newtons or newtons and meters. It all, that's where the physics throws in those little details for you. Okay, any questions on that one? Are you dizzy yet? No? Maybe a little music might help us out right now? No? Was it music or a movie?
I think it was, it's on.
Okay.
But I don't think it was.
Okay. Consider a region D containing a hole as shown here. All right. I'm going to draw this over here. Or you know what? I'm going to draw it right here. Okay, there's D. All right, just want you to consider this for a second. I'd like to use Green's theorem here. There's a problem, though, that my region is not simply a simple region, right? Because of that hole in the middle. So I'm going to define two curves here. C1, which is going to go around the outside like this. And then C2, I'm going to do in a different color, which will be going along the inside. Oh, wait, hold on. That last problem, negative 16. I forgot to change the sign. Right? Okay. So the other one, I wanted to go clockwise. All right, and I'm going to call that C2. Okay? Now, what I need you to do right now with this is just follow me, all right? I'm going to get to a final conclusion, but you just got to follow me for a little while. The big question here is, what would the double integral over D, hold on, make sure I'm stating this properly. Back to my notes. Yeah. Double integral of D of partial Q with respect to X minus partial P with respect to Y B dA. So ultimately, I'm going to ask myself what this is, all right? The problem with D is that it has a hole in it. So I'm not quite sure about how the green's going to work, or if it's going to work. So I'm now going to take this, let's see, I have green, I have some green in here, and I have purple. I'll take them both in case one of them doesn't work. All right. Here comes a new curve. Just going to pick that point right there. I'm going to imagine cutting across here and then going up and over like this. And then back here, and then over and back. You see that piece right there? I'm going to call that J. That's a new curve. And the orientation on J is the same as C1. J. All right? That's J. So J goes up and over that, and then across like that. Got it? Okay. I'm going to break J. J is a closed curve, isn't it? J is a closed curve, and it has positive orientation, and it encloses a solid, doesn't it? The solid that it encloses, I'm going to call D1. Okay, D1 is the solid that's just this top half. Does D1 have a hole in it? D1 does not have a hole in it, does it? Okay, so I should be able to use Green's theorem on D1. All right, next thing I'm going to do is I'm going to draw another curve. This one, I'm going to start here. I'm going to go backwards this way, down across like this, across like this, down, and back up like that. And we're going to go also in positive orientation, isn't it? And I'm going to call that one K. It's the path K. And do you agree that the path K encloses a region? I'm going to call that D2. Right? So, we learned about double integrals over regions, that these are also, if you can split the region up into two smaller regions, that it should be this plus this. All right. So y'all buy that? Okay, so I have D1, D2, the union D1, sorry, D is equal to D1 union D2. So the double integral over D should be the double integral over D1 plus the double integral over D2. I keep going. D1 doesn't have a hole. You said I could use Green's theorem then, right? So this, by Green's theorem, is the line integral over the closed curve what? So D1 is this one, which was J, right? So this is the line integral over J of P dx plus Q dy, right? Y'all still there? Plus the line integral over the closed curve what? For D2 it's K P dx plus Q dy. All right. Any questions so far? We're getting there. We're not there yet. We're getting there. Remember, this problem started out with me giving you C1 and C2, right? I gave you C1 and C2, right? And we were talking about this D in here. I have somehow said that the double integral over D is going to be the line integral over J and over K. I'm going to try and get somehow J and K back to C1 and C2. So here's how I'm going to do it. I'd like to look at J as being the union of a bunch of smaller paths. So you see J is this whole thing, right? All the way around like this. So it's going to be very difficult for me to do this, but I'm going to try. Let's call the little path that goes from here to here, let's call that little j1. Okay? And then the path that goes from this point all the way around here, let's call that little j2. And then the path that goes from here across here, let's call that little j3. And then the path that goes from here to here, little j4. Understand? So this integral right here, I wish I had more room down here, but I'm going to continue it up here. This J line integral, right, is actually, this right here is the line integral over J1 of P dx plus Q dy plus J2, J3, or little j1, little j2, little j3, little j4 all added up, right? So I'm going to start not writing all this out because this is a pain in the ass. J2 dot 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 plus J3 dot 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 plus J4, right? Dot dot dot. That's this piece. Plus, so now I'm going to move to this piece. I'm going to break K up into smaller pieces. Let's call this from here to here, call that K1, little k1. From here to here, little k2. From here to here, little k3. And then from here all the way around, little k4. Y'all still alive? Maybe we should have that music in the background. I feel like maybe we need it. So this one is line integral over what? K1 plus K2 plus K3 plus K4. Yeah? Does anybody see what is about to happen?
Oh, you're going to combine.
What about J1 and K1? What about them? They're opposite directions. Same path, opposite direction, which means they cancel. So this integral right here, this line integral, is going to cancel with K1. Right? Anything else cancel? J3 and K3 from here to here are also opposite directions. J3, K3? J3, K3 are gone. All right. So now we're so damn close. Can anybody tell me, in terms of J and K, what C1 is?
K4 plus J2.
So C1 is this outer one, right? Like that? And that's just from here to here, that's J2, and then from here to here, which is K4. So J2 and K4 are really just C1. Yes? So I'm going to continue next line. This equals, so that equals the line integral over C1, right? This time I'll write it P dx plus Q dy plus, what's left? J4 K3? No, J4 K2. J4 along with K2, right? J4 along with K2 is what? Oh, sorry, I'm going like this. I meant to go J4 along with K2, right?
Yeah.
Is what? Not C2. Well, wait, hold on. I drew C2 in that direction. Sorry. I did draw it in that direction, right? So isn't that C2?
Yeah.
Yeah. So this is we're done. Here's what we just did. We just said that if you've got a region with a hole in it, all right, D, then if you call the path going this way C1, and you call the path going this way C2, then the Green's theorem can be applied to this, and this double integral of partial q with respect to x minus partial p with respect to y is just the line integral over C1 of p dx plus q dy plus the line integral of over C2 of p dx plus q dy. All right? Big deal, right? Who cares? So I'm going to show you, we're about to use this now for a problem. All right? I hope that made sense. As many times as I've tried to explain that to people, this part right here, that actually, believe it or not, felt like one of the better presentations of that. Like, I think some of you, most of you got that. Here it is. I really like this problem. Show that the work done by the field F over the curve C, or as you move something along the curve C, is always equal to 2 pi. If I give you the field is this, and C, that should be C1 up there, sorry. Make this C1. Where C1 is any closed path that encloses the origin. Any closed path that encloses the origin. So what's difficult about a problem like this is that you don't have C1. Like, they don't tell you what C1 is, right? You're actually trying to show that you'll always get 2 pi no matter what closed path you pick, as long as the origin is inside your path. So if I take any path, as long as the origin's in here and I do the line integral over this, the answer is 2 pi. Someone else comes with a different path. That one, as long as the origin's in there, the answer is 2 pi. Right? The answer is 2 pi. Now, you could pick one path if you wanted to and show it's true, right? That's not what it's asking. It says show it's 2 pi for every path that encloses the origin. So how in the world would you ever go about attacking this, right? Seems like it would be impossible. Does it not? Seems somewhat unreasonable to expect you to check every single path when that's impossible. So how would a mathematician actually show this? Here's how we do it. All right. Here's how we're going to do this. We're going to draw our picture, and we're going to pick an arbitrary C1. Here it is. This is completely arbitrary. I could have drawn it however I want to draw it. You draw it however you want. Okay? So we're going to call this C1, and we're going to orient it positive orientation. There we go. The origin is in there, right? Completely arbitrary path. I will never be able to give you the parametric equations for these because I don't know what the path is, right? It's arbitrary. Now, if the origin is in here, this is the key point. If the origin is inside there, then do you agree that there is some smallest, like minimum distance between my path and the origin? Like there's some space between my path and the curve. Some value, whatever. Well, what I'm going to do now is I'm going to choose a new path. And I'm going to call it C2. And it's going to be a circle that's inside the curve you just drew. All right? So the circle I'm going to choose is going to be a circle that encloses the origin and has a radius. I'm going to call that radius A. All right? And here's the condition, is that this radius, I'm going to choose it small enough so that my path is inside your path. Do you believe I can always do that? Like if you hand me a C1, do you think I can then find another path inside your path that still encloses the origin? There's got to be some space between there, right? Okay. I can always take like the smallest distance. Like if this is the smallest distance between the origin and your path, I can always take my radius to be half of that distance. And then I'd still be there. So thanks to the real numbers, we can always take a number halfway and we never get to 0. So, all right, got that? Now, I'm going to orient this one negative direction. I'm doing that because of the thing we just did a second ago. Remember the picture I drew a second ago? We had our shape, we had our missing thing, we called C1 was this way, and then this one was C2, right? And then we said here was the region closed D, right? All right, so let's talk about what this is. What is this? D is going to be the region between these two, right? So outside this circle, inside this. Oh, and I never called this C2, did I? C2. Okay? Well, we have the field, don't we? We have our actual field here. Okay, so let's calculate this. This is the double integral over D of the partial of Q with respect to X minus the partial of P with respect to Y. This is a little harder to get these partials, right? These are not as clean. So let's do them on the side. What is the partial of Q with respect to X? So this is Q, this is P. So what is the partial of Q with respect to X? Don't we have to do like a quotient rule? So derivative of the top, which is 1, times the bottom, minus, what's the derivative of the bottom with respect to X? 2x times the top, negative y, so that's going to make that plus y like that. Then all over the bottom squared. So just a quotient rule on Q, right? Taking derivative with respect to X. Let me clean that up a little bit. X squared, I don't really need those parentheses, right? Plus y squared plus 2xy over x squared plus y squared squared. Do not cancel those, please. Do not do that. All right. That's partial Q with respect to X, right? Yeah. Now, let's find the partial of P with respect to Y. So that means derivative of the top, right? With respect to Y, which is negative 1, right? Times the bottom. Minus derivative of the bottom with respect to Y, 2y, times the top, y, right? Negative y? So plus yes or no? I mean, y'all seem befuddled. Quotient rule on this with respect to y, right? So what is that cleaned up? Oh, wait a minute, hold on. This, let's see, this top, derivative bottom. Yeah, no, that's it. So what do we get on the top there? Negative x squared minus y squared plus 2y squared all over x squared plus y squared squared. I'm hoping y'all are all looking at me crazy, so did I mess something up? Which one, this one? This one up here? Derivative top times the bottom plus derivative of the bottom with respect to x times the top. Is that what you're talking about? That right there should be x.
Yeah.
Yes, that's x. Y'all, well, at least I recognized that y'all all had that look on your face, like something was up. Yes? Okay, that changes a lot of things here. Because now when we combine these, this is actually what? 3x squared plus y squared. Okay. And then is this one right? Derivative of the top with respect to y times the bottom minus the derivative of the bottom with respect to y times the top, but the top is negative y, so makes that a plus. So what does that turn out to be here? This one is going to be I feel like we're messing something up. 2y squared, so this is negative x squared plus y squared over x squared plus y squared squared. Something is off.
You could take the negative out of the front line and end up canceling out, so that we have negative 1 over x squared plus y squared.
What are we going to get when we put these together? When we do partial of q with respect to x minus partial y, or partial p with respect to y. Oh, you know what? I think I see it. I think I see it. Is this right with a plus? That's a minus.
Yeah.
What happened was when I was looking from here up doing the partial, I looked right here. That's what I did. I went to this one. So can we just run through that again?
Yeah.
Okay, let's just run through this one again. The partial of q. Don't freaking look at that, okay? Partial of q with respect to x. So you take derivative of the top with respect to x, which is 1, times the bottom. Okay, minus the derivative of the bottom of that with respect to x, which is 2x, right? Times the top, which is x, all over the bottom squared. All right, now, the next line, cleaning that up, you get x squared plus y squared minus 2x squared all over the denominator, right? And then the next line would be y squared minus x squared over the denominator. We'll say that denominator squared, right? So that's it?
Yeah.
And then this one is this one. And I think that one's right. So now let's plug everything in. The partial of q with respect to x is going to be y squared minus x squared over the denominator squared, then minus this one, right? Minus this one, but when I subtract this one, it's going to change the signs. So it becomes, well, I'll just do it here, minus x squared plus y squared over the same denominator squared. And I think you can see there what happens. The numerator becomes 0. And so this whole thing is 0. Right?
Yeah.
Wait a minute, I thought the answer was supposed to be 2 pi. No, that has nothing to do with what we're doing. What I did is I said, hey, what is this double integral over d of this equal to? Everyone agree it's 0? Okay. However, by what I just showed you before this, what is this in terms of line integrals? This is the line integral over the closed curve C1 of p dx plus q dy plus the line integral over what? C2 of p dx plus q dy, right? That's what this is. This is this, but what's this? Is 0. So this is 0, isn't it? Well, that still doesn't tell me anything, right? Well, isn't this what we're looking for? Yes? And if this plus this is 0, then these are the same, they're just off by a sign, aren't they? This, though, is the line integral over C2. And C2 is a circle that I can come up with the parametric equations for. So I can actually calculate this line integral. And whatever it is, that answer is equal to the opposite of this answer. So my next line is to show that I have this. I have the line